Hello. Right. Okay. Hello, Mia. Hello, Edward. Not too many people. Good. So, okay. So today I wanted to do half and half. So as you probably saw in the topic of the webinar is that some of it is going to be dedicated to simple harmonic motion, and some of it is going to be dedicated to series. Mostly it's going to be Taylor series today. Since there's only two of you at the moment, what's it like? So you've been doing assignment 10. Which parts did you find the most challenging?
I've done assignment 10 for maths, but for physics, I'm halfway through.
Okay. Okay. So what was the most challenging bit in maths?
Taylor series.
Taylor series. Okay. Do you think you've managed to do them?
Yeah, I think so.
Okay.
Yeah, pretty much.
Good. Okay. And what about you, Edward?
Yeah, same. I've been doing the physics and maths ones like at the same time. So I just literally now started doing Taylor series, and I find them really hard. And also the simple harmonic motion problems later on in the problem set are also really get a lot more challenging later on.
They do, but okay. So I think I've chosen the problems quite right because you're in similar situations. Yes, we are going to go through Taylor series. I'm going to show you that it's actually not that hard, and then we'll and that's going to be the second half of today. Okay, welcome Adam and Thomas. So I'll start sharing my screen. Oh, can I? Oh, I guess I can share my screen like this. You should be seeing my screen. If not, let me know. So we start from a not very difficult problem on simple harmonic motion. And so what this is about. So we have a trolley which is traveling towards a spring. And when the spring is compressed by L, the trolley becomes momentarily stationary. Find the time it takes to stop the trolley. It's quite interesting because we're only given V and L. And let's see if that is enough. So what's the link of this question to simple harmonic motion? Can somebody help me? Can somebody tell me? Like, why is this question even in this topic? The trolley won't be decelerating. Yes, it stops, it flies back. Doesn't look like simple harmonic motion. Well, as a matter of fact, it is, well, it's a half. It's a half or a harmonic, and then so it travels at constant speed, then half a cycle of a harmonic. Yeah, so it takes a quarter of a harmonic to stop, absolutely, and that's what we're going to use today. And here we are. So what do we know about the harmonic motion? So imagine the trolley sticks to the spring and it starts bouncing back and forth. So obviously we know the initial speed, which is the maximum speed. So the maximum speed is v, and this is the speed that occurs when it touches the spring. And we also know the amplitude. The amplitude is L. Okay. And well, it seems like there's not enough information to do the question. But as a matter of fact, we know that the maximum speed is given by the expression omega A, omega times the amplitude. It's quite easy to prove because we know that in simple harmonic motion, x is amplitude times sine omega t, and velocity is the derivative x dot, which is a omega cosine omega t. And the maximum value occurs when, because cosine can only take values between -1 and 1, the maximum value is when cosine is 1. So Vmax is a omega. Right, and using that, it's very simple. So omega is going to be V divided by L, and therefore we have 2 pi over, so T, time period, is equal to 2 pi divided by omega, so 2 pi divided by V multiplied by L. And that's it. That's the time period. It's 2 pi divided by omega, which is 2 pi L over V. So as a matter of fact, we can figure out the time period, even though all we know is the initial speed and the amount by which the spring is compressed. Okay, does it make sense? Any questions? Any questions about this? So this is a question of mostly just understanding that simple harmonic motion occurs in some situations where it's unexpected. Nobody expects simple harmonic motion from a seemingly simple situation. Well, that's the time period. The time it takes to stop is going to be t over 4. Yeah, sorry. So the time it takes to stop is, of course, t divided by 4, which is pi L over 2V. Yeah. It's a quarter of a time period. Thank you, Adam. The next question, a box of mass m, so we have a heavy box of mass m, has an oscillator. What is the minimum amplitude of the oscillation that the box starts to jump on the table? What is the minimum amplitude that the box starts to jump on the table? So basically, if the mass moves with a high amplitude, at some point we will see that the box begins to jump. Okay. So like how would you approach this problem? which two things would you compare, or how do you even start? You can use the mic if you have something to say. If you have any ideas, any idea is valid. If you want to try and help me with this, like, what would happen? What would happen when the box jumps? Why would it jump? Why would the box jump?
The force from the spring is greater than the weight of the box?
Absolutely, yeah. It starts to jump if the force in the spring, is greater than mg. Okay, is greater than mg. And okay, when the force in the spring is greater than mg. And we know that for the smaller mass, so for the big mass, yeah, of course, there is actually I'll do this question a little bit more formal than just saying that the force of the spring is greater than the mg, because there are three forces involved. There is the mass, the mg, the box. There's the normal reaction force from the ground. And there's the force of the spring. The force from the spring will sometimes be up, sometimes down, but we are obviously interested in when it is compressed. That means at its maximum position. Therefore, we are interested, yeah, when it's compressed at its maximum position. Okay, so this is the force of the spring. This is mg. And this is the normal reaction force. The box starts to jump when normal reaction force becomes 0. And because if the box is stationary, so N plus F is equal to mg. And very formally, I say box jumps if the normal reaction is 0. And that means that F is equal to mg. Or in other words, F is greater to mg. Okay, good. Right, let's say, what do we have here? So all we need to do is find the force in the spring, and the force in the spring is obviously equal to kx. So now we look at the oscillator, at the mass, and so when the oscillator is compressed at its maximum position, so we have the equilibrium position. Equilibrium position. Now, interestingly, in the equilibrium position, there is still a force in the spring. So we have another position, which we call the unstretched position. Unstretched position. Unstretched position. Because when we add the mass, the spring stretches, of course. And we can find this. We can find this extension. Let's call it x0. x0. And this is the unstretched position of the spring. That is, we have mg equals to kx0. So when the spring is hung stationary, so x0 would be mg divided by k. Okay, that's the first piece of the puzzle. Now we can do the amplitude. So the amplitude is the maximum, is the furthest out position of the spring, of the box, sorry, of the smaller box. So let's call this the amplitude A. Amplitude. Okay. And we know that the force in the spring, is equal to K multiplied by X. In the maximum position, in the extreme position, it's Ka. Right. Ka. Oh, sorry. That's not exactly right. The force in the spring is equal to K multiplied by the extension. But the extension is not A. The extension is A minus x0. K multiplied by A minus x0. That's important because in the extreme position, in the top position, the true extension of the spring, which gives you the true force in the spring, is actually is A minus x0. It's not A. It's not the extension of the spring. And we can substitute. We just substitute what we know. Right. So the force in the spring has to be equal to mg. And the force, as we know, it's K multiplied by A minus x0. x0 equals to mg. So Ka minus kx0. And kx0 is mg. x0 equals to mg. So Ka minus mg is equal to mg. So Ka is equal to mg plus mg. So amplitude is equal to fraction m plus mg divided by k, and that's the answer. Okay, that's the amplitude. Okay, the next one. The next problem is a problem which you might have seen. Well, you might think you have seen it, because 2 springs and an oscillator seems reasonably straightforward. However, the difference in this question is that there is a pulley. There's a pulley involved. And it's not the same as having 2 springs attached to the ceiling, for example. If you have 2 springs attached to the ceiling, that would be reasonably straightforward, because you know that the spring constant of both springs. The spring constant of two springs in parallel is K1 plus K2. So it is very straightforward to find the period of oscillation in this case, but it's not that case. So like with any unknown system, what we do is we displace the mass by a small amount and look at the forces involved. So let's say this is the equilibrium position. We direct the x-axis downwards. We say this is the x-axis. So we displace the mass by a small amount, x. And we need to find the forces that appear as a result of us moving the mass down. Okay, so it's Newton's second law. Newton's second law. So the mass times the acceleration is equal to the two springs. So minus kx1 minus kx2. K2, sorry, K1 x1, K2 x2. No, the mass would not tilt clockwise or anti-clockwise. The mass would not tilt clockwise or anti-clockwise because for this to happen, you would need an imbalance of the forces. And an imbalance of the forces is only possible if the pulley has mass. The pulley can provide a moment. But because the pulley is massless, it cannot provide a moment for the spinning of the for the spinning. Right. Now, but what do we know? Do we know anything about x1 and x2? Perhaps. I mean, it would be a I've got you. I've got you into a trap. I mean, I have set up this trap for you, and I've got you into a trap. It seems like x1 is equal to x2 and equal to x, but it's not, because the pulley acts as to equalize the forces. The tension in both springs has to be the same because of the pulley. The pulley will constantly equalize the forces in the two springs. That's what a pulley does. It provides the same tension all around the rope. So it's not, because if the extensions were the same, that means with different Ks, that means they would have different forces, and you can't have different tension in a single rope with a massless pulley. With a pulley with mass, it's possible, but that's a whole other story. That's a whole kind of worms we're not going to open. But as a matter of fact, what we actually do know is that x1 plus x2, the total extension of both springs, is equal to 2x. That's a thing that we do know. Or in other words, the extension is the mean extension of the 2 over 2. That is what we do know. Okay. Another thing I have already mentioned is that the forces have to be the same. Oh, I mean, the second statement is pretty useless here, but anyhow, we know that the forces have to be the same. K1x1 has to be the same as K2x2. I'm not really concerned with the signs here. I'm working with the absolute values here. And from here, we can say that x2, for example, x2 is k1x1, k1x1 over k2. k1x1 over k2. And I sub that in. I sub that into here. And what do I get? Is I get that x1, open bracket, 1 plus k1 over k2, multiplied by is equal to 2x, is equal to 2x, and yeah. So from here, I can say that x1 is 2x k2 over 2x k2 over k1 plus k2, k1 plus k2. This is x1. X. I think it's quite easy to guess what x2 is going to be, but yeah, so it's x2. x2 is going to be a very similar expression, but with k1 instead. x1 and x2. Now we sub that in into our Newton's second law. So from here, I can do ma is equal to minus k1 x1. So it is minus 2k k1 times that. So 2k1 k2 times x minus so it's going to be k sorry, what happened? x2 is 2k1. Okay, x2 times k2 is going to be the same. It's the same thing, and it makes perfect sense because, as I said, the tensions have to be the same. That's why these two expressions are perfectly equal. So in other words, we have MA is equal to minus 4 minus 4 over that, and acceleration is equal to, sorry, K1, acceleration is equal to that divided by M. Okay, looks a bit scary, but actually all what I have done is I've displaced, and this is your approach always. This is your approach when you're doing simple harmonic motion. Your approach is you take your mass, you displace it by a small amount, you write down Newton's second law, and then I'll show you what you do next. So you have acceleration, and as you know that for simple harmonic motion, acceleration is equal to minus omega squared x. So from here, I can see that omega squared is that fraction. This is omega squared. So from here, I can see that omega squared is equal to that. And from there, I can work out the time period. The time period is 2 pi divided by omega, and that is 2 pi divided by omega. Well, it's going to be 2 pi divided by 2, so it's just pi square root, and then we have mass K1 plus K2 divided, that is not good, two pi, so it's pi square root fraction. So it's going to be M K1 plus K2 divided by K1 K2. Yeah, I think I haven't missed anything. So that's the time period. The 4 cancels with the 2 pi. Okay, so time period is 2 pi over omega. So what I did and what I do, as I've already said several times, I displace this mass by a small amount. I write Newton's second law. I find the acceleration in terms of x, in terms of the displacement, and I compare it to this equation. This is how you do any problem on here. So let's have a look at the assignment. So what do we have here? Simple harmonic motion. So find, like here, like this problem. This problem, what you do is you select a single mass, You displace it by a small amount. You displace it by a small amount. You write the Newton's second law for that mass. You will have an expression, something like ma is equal to minus something x minus something x, and that something is your omega squared times m. Okay, does that make sense? Let me know in the chat if that makes sense. Displace it by a small amount, x. And then you see what forces are involved. And that force is, in that expression, is your omega, the one that you're looking for. Here, I think I've told you, I've shown you last week 2 weeks ago how to do that. Same thing here. Well, here it's very difficult to find the. It's very difficult to do the acceleration here. But what you can do is find the energy. So when you displace it by a small amount, find the energy change, and you find the potential energy in terms of x. Potential energy in terms of x, and then you compare it to the standard equation, and that's it. Oh yes, you compare it to this one. You compare it to this equation. So what you have, you move the oscillator slightly to one side, any side, it doesn't really matter which one. You find the expression of v in terms of x squared. You compare it to that, and that's your answer. That's how you figure out omega. Okay, moving on. All right, so the Taylor series. The Taylor series might seem scary at first, and at second thought, but you really want to ensure you understand what each term is in here. Okay, so I'm just going to do I'm just going to write out the Taylor series for sine x, the most commonly used expression. So sine x is equal to. Now we are saying in the vicinity of 0. We're saying that when x is 0, so it's going to be, let's say f of x is equal to sine x. All right. So what we need? We simply need the derivatives. We need the function of 0, f of 0, f of 0. So sine 0 is 0. Now we need f, the first derivative of 0 is the derivative of sine is cosine, and cosine 0 is 1. Then we need the second derivative. Second derivative of 0 of sine. So the second derivative of sine is minus sine, so it's minus 0, so it's 0. This the third derivative of sine at 0 is minus cosine, and minus cosine 0 is minus 1. Does this make sense so far? Like, do you understand this out of 10? Do you understand what I did here? Out of 10, so 10, yes, yeah, okay. And all you need now is to plug those into your formula. So this is your formula. So I'll copy that. And we see that f of x is equal to f of 0, so 0, plus f stripe of 0, so it's 1, multiplied by x, plus 1/2 multiplied by multiplied by 0, multiplied by t squared. Well, that's still going to be 0, plus 1/6, so 1 over 3 factorial, as a matter of fact. It's not technically 6, it's 3 factorial. And this is 2 factorial. 2 factorial. 1 over 3 factorial multiplied by -1. -1. And multiplied by t cubed. Plus etc. And it turns out that this is x minus x cubed over 3 factorial plus etc. It's an infinite series, like an infinite geometric series. Well, it's not geometric, but it's similar too. Okay, and if you notice the pattern, you will clearly see, because the derivatives are going to go 0, 1, 0, -1, 0, 1, 0, -1, etc. So you can continue this series as much as you want. So it's going to be x to the power 5 divided by 5 factorial minus x to the power 7 divided by 7 factorial plus etc. The more terms you give, the closer you are to sine x. So the key thing to take away from here is that this is f of x. F of x is sine x, which is approximately equal to that. But if you say plus etc., if you don't limit yourself, then you can say it's exactly equal to that. It's exactly equal to that. I prefer approximately. Why is it? Okay, I prefer approximately. Anyways, if you have ever done some sort of computer programming, so type 1 if you've done computer programming, and type 0 if you haven't. You know, like if you do a very simple language, if you use a very simple computer language, like assembly language, you'll probably understand that a computer is very good at adding numbers. It's very good at multiplying numbers, subtracting numbers, reasonably good, dividing, reasonably good. But because all these things are inherently present in the way the computer does its operations, the operation of adding is very well defined. It's very understandable by the computer. But let's say you want the computer to find a sign of something. How do you even begin to explain to the computer that sine is the opposite side in a triangle divided by the hypotenuse? The computer has no concept of that. So computers use this instead of sine. So whenever you type sine 23, whenever you give a computer sine 23, Instead of doing sine 23, it gives you, it takes this function. It says that I know that sine is approximately this, and I'm going to use that. And let's see how close. You already saw how close it is. You already saw how close it is in the assignment. I'm just going to demonstrate it to you again, and how you can see that on Desmos, for example. Okay. So I'm going to start with y equals sine x. And that's easy to see. And now I'm going to go y equals x. And you see that y equals x is quite close to sine x in the vicinity of 0. In the vicinity of 0. It's quite close. If you do x minus x cubed over 3 factorial, it gets even closer. And then you do plus x5 over 5 factorial, and it gets even more so closer to the original function. Minus x x to the power 7 divided by 7 factorial. And the more you do that, so if you keep doing it forever, the two functions will line up perfectly. And we do say that when x is close to 0, sine x and this function vary very little. And this, for a computer, this is almost impossible to understand. And this is incredibly easy. Like multiplying a number by itself 3 times and dividing by 6 is a very easy task for a computer, even for a very basic one. Okay. Now, let's look at the second equation, the second formula. Show that the graphs of sine x and the Taylor expansion behave in a similar way near x0. Now, let's see what happens if we take this point near x equals pi over 6. As you can see, apologies. Right. So as you can see, pi over 6 is roughly okay. I think I might make my life a little bit easier. I'll just take a more significant value, because pi over 6 is rather small. You won't see a difference. Let's do a slightly different question. Near 2 pi. Okay. Near 2 pi. All right. And now I use the second formula. Let's see what's the difference. And the difference is that you need to substitute not the 0 value, but t0, which is 2 pi in this case. So we find f of 2 pi. F of 2 pi is, sorry, just copy that. F of 2 pi, it's still sine. We're still talking about sine. So f of x is equal to sine x. F of 2 pi is sine 2 pi, which is 0. Now we need f prime, F double prime, F triple prime, F the fourth derivative, the fifth derivative, and the sixth derivative. We usually write like this: 6, 6, 5. Brackets indicate the derivative. Fourth. Okay, so the first derivative is cosine, of course, and cosine of 2 pi is 1. So the pattern is going to be the same, but just because I chose 2 pi. Minus 1, then it's going to be 0, then it's going to be minus 1 and 0, 0, and etc. And now I use this formula. I say, okay, so it's going to be, so f of x is approximately equal to f of 0, f of 2 pi, which is 0, plus. Now here we have 1 over, well, it's going to be, okay, I'll write it out, because f of 2 pi plus, it's going to be f prime of 2 pi multiplied by x. Well, not by x, by x minus 2 pi. Okay, plus f double strife of 2 pi multiplied by x minus 2 pi to the power of 2 divided by 2 factorial. 2 factorial. Okay. Plus f 2 pi divided by 3 factorial. And here we have x minus 2 pi to the power of 3 plus etc. And here we have f of x approximately f of 2 pi is 0 plus f strife of 2 pi, so 1 times x minus 2 pi, plus 0 plus minus, and it's going to be minus 1, so x minus 2 pi to the power of 3 divided by 3 factorial plus etc. So in other words, f of x is approximately x minus 2 pi minus that Right. So what I have done here, plus etc. It's pretty much the same series, but instead of x, we have x minus 2 pi. What we are doing here is we are approximating as f of x equals sine x in the vicinity of x equals 2 pi. And let's see what it does. We're going back to our Desmos graph. I'm going to hide this one. And I'm saying y is equal to x minus 2 pi plus a minus fraction. So x minus 2 pi cubed over 3 factorial plus, you can guess where this is heading, 5 over 5 factorial, and it's going to be plus. And you can see that now what we have is an approximation, but at a different point, not at 0. Initially, it was an approximation in the vicinity of 0. And now this is an approximation in the vicinity of 2 pi. You can see that 2 pi is now the center of attention. But regardless, if you keep doing that, the two graphs will perfectly match up. It's just if you do it in the vicinity of 2 pi, well, if you need an approximation in the vicinity of 2 pi, you would use this formula rather than this formula, even though these formulas are equally valid. It's just this is a much better approximation than this one. As you can see that at 0, they're nowhere near. The two graphs are nowhere near. But at 6 or 7, they are very close. Have I managed? So my aim was to provide a better understanding of what the Taylor series is about. Do you have a better understanding now? So type on a scale of 0, 0, 0. Well, yeah, probably a yes or no. Yes or no question. Yes. Okay, good. So Taylor series is all about taking a complicated function and turning it into something very simple, like a power series. A power series is something very simple. And especially for technology, when you're trying to make a computer work with complicated functions. And okay, so I've shown that these two functions are very similar. Now let's have a look at this. Evaluate a limit using a Taylor series. You saw that we had the questions like this in the assignment. It's the last questions. And you saw these pictures, so they're not here. They're not a coincidence. These are incredibly useful. These are incredibly useful, and they are actually worth memorizing. It will really help you if you memorize these. Because we know that sine x is approximately x, cosine x is approximately 1 when x is small, of course, when x is small. When x is small. Now, by now you understand that x is small is another way of saying in the vicinity of x equals 0. It's a Taylor expansion in the vicinity of 0. Okay. So the Taylor series, we see that x tends to 0. So we are only interested in the function very close to 0. We're not interested in what happens for large x's. And well, if you try to find it straightforward, if you just plug in 0, use x equals 0. It won't work because e to the power of x is 1. E to the power 0 is 1. So it's 1 minus 1 minus 0 divided by 0 squared. So it's 0 divided by 0. It's not. So we have a 0. We have 0 divided by 0. So you can't do it. So what you need to do is to approximate this, and from the previous week, you probably saw that e to the power of x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. E to the power of x is approximately this. What you do is you use this in here. It's equal to the limit. Nope, that's not what I wanted. The limit as x tends to 0. Now, instead of e to the power of x, I'm going to write 1 plus x plus x squared over 2 factorial plus, and just in case, I'm going to write x cubed over 3 factorial plus etc. minus 1 minus x divided by x squared. Now, as you can see, 1 and x cancel. 1 and x cancel. And you are left with x squared over 2 factorial. And the trick you can do here is to take x squared out of the brackets in the top x squared in the numerator. This becomes 1. This is x to the power 1, etc. Divided by x squared cancels. And it's going to be going to be limit of 1/2, limit of 1/2 plus x over 3 plus 3 factorial, sorry, so 3 factorial plus x squared over 4 factorial plus etc. But now you can substitute x equals 0 into this. You can substitute x equals 0, and you can see that the whole thing is this. These are all going to be zeros. This is all going to be 0. Therefore, the answer is 1/2. 1/2. So what you did here, you had a limit which was not solvable straight away. You approximated the behavior of a function by the Taylor series, and that's it. A very similar situation happens here. Sine x over x. We know that sine x is approximately x plus x cubed over 3. So this is going to be x over x. Yeah, so this is approximately x over x. So the answer is going to be 1. It's a very common. It's called a wonderful limit, or interesting limit. Now, let's have a look at this one. Show that. So let's look at problem 19. I'm not going to do problem 19, but I'm going to do a similar one. I'm going to do a similar one. This is going to be. Do you have time? And maths. Oh wow. Yeah, the last one is tough. But hopefully this one give you some insight on how to do that one. From the series of, so I'm going to find show that. I'm not going to do that, of course, but I'm going to find the expansion of cotangent x approximately. Okay. Well, as a matter of fact, you could do it straight away. You can find the expansion of tan just using the thing I did here. Is just instead of sine, you use tangent. And it is going to work, and it will give you this result. But they're asking, take the known expansions for sine, cosine, and this, and show that this is true. So how does that work? So I'm going to do cotangent. So I'm going to do cotangent. We know that cotangent is cosine over sine. Cosine x divided by sine x, which is in turn cosine x multiplied by sine x to the power -1. Cosine x multiplied by sine x to the power -1. So let's write out what we know. We know that cosine x is x to the power, so 1 minus x squared over 2 factorial, well, over 2, we don't need, so plus x to the power 4 over 4 factorial, which is 24. 24 plus etc. We don't need more. We need sine. Sine x is x minus x cubed over 3 over 6 plus x to the power 5. I really hope I won't need that. 20 plus etc. And 1 over 1 Oh, that might not work. We need a 1 there. It will work. 1 over 1 plus x. 1 over 1 plus x. 1 over 1 over 1 plus x is 1 minus x minus x. I believe it's going to be x squared minus x cubed plus x to the power 4. Now you can cheat sometimes. Expansion of you can use the binomial theorem, of course. It is, yes, 1 minus x plus x squared minus x cubed. You can use the binomial. You can use the binomial formula here as well. 1 minus x plus x squared minus x cubed. Brilliant. So how are you going to how do you propose to find cotangent? Cotangent x is cosine x. So we take the expansion for cosine x. Yes. Take the expansion for cosine x. Okay, and we multiply it by the expansion of, well, it's going to be sine x. We need this. We need the sine x. Sine x to the power minus 1. So it's going to be 1 divided by sine x. One divided by that. Now this is straightforward, but this is not. So I'm going to write this out separately. So here, I'm going to take 1 over, and I'm going to take x out of the brackets. And what I will have minus x squared over 6 plus x to the power 4 over 120 plus etc. So 1 over x, well, yeah, that's easy. And now what the hardest part here, the trickiest part, is seeing that this, in fact, is this. if you do a substitution, x, well, u is equal to that. Do a substitution. And now, okay, this is a bit, it looks a bit clumsy in a way, but you have this multiplied by this, which is the same. This multiplied by 1 over x and multiplied by the expansion of this, thing. Oh, not this thing, sorry. Multiplied by 1 over x and multiplied. So I'm going to use this expansion. I'm going to use this and the substitution. So yeah, okay. I'll try to make it as detailed as possible. So 1 over 1 plus u. 1 plus u is of course 1 minus u plus u squared minus u cubed plus u to the power 4. Plus etc. 1 over that. And because we have this substitution, and that means that 1 over 1 plus this monster one plus that is 1 minus that plus that squared plus minus that thing cubed plus that thing to the power 4. Now, don't be alarmed. I don't have to expand every single bit. All I need is to expand up to we only need powers up to 5. Or no, we cotangent is a cotangent is an odd function as well. So yeah, powers up to 5. Powers up to 5. And how do we get that? So it's 1 plus x to the power 2 over 6. X to the power 2 over 6 minus x to the power 4 over 120 plus, now the next one, the first term is going to be the 4th power. So it's going to be x to the power x to the power 4 over x to the power 4 over 36. And look, this is to the power, this is to the power 4. This is going to be to the power 8. So we're not interested in that. This is going to be 6. This is 8. 8. Sorry, not even 8. Yeah, 8, 16, and that's it. So we only need up to the power 4 plus etc. Now, it looked very scary, but it's not. It's just that. So you take that and you substitute into your original expression. Equals 1 on x times open bracket. And now you start multiplying. You start multiplying these two brackets, but you only need up to power 4. So it's going to be, so you choose not even power 4, up to power 3, as a matter of fact. But it's fine. So 1 times 1, that's 1, minus, so 1 times x to the power x, so x power to power 2 over 6, minus x to the power 4 over 120, and oh, there's another x to the power 4. Okay, plus, I should have simplified that. Anyways, x to the power 4 over 36 plus, so it's minus x squared over 2, and then it's going to be minus x to the power 4 over 12. That's this one and this one. And finally, yeah, and finally x to the power 4, so plus x to the power 4 over x to the power 4 over 24. So then you simplify that, and you get an expansion. You get an expansion in terms of x. Now, I might have made a mistake somewhere here, but this is going to doing tangent is easier, and it's going to be using the same principle here. So x 1 over x. I should be getting rid of the 1, so I'm not sure why I'm not getting rid of the 1. Yeah, well, you expand this and you get your expansion for cotangent. Oh, I think the expansion of cotangent in the vicinity of 0 doesn't really exist, because you're dividing myself, of course. Sorry, I think I've made a massive error in the very beginning of my question, because cotangent cannot be, because cotangent does not exist in the vicinity of 0. It's cotangent can only be in the vicinity of, let's say, pi over 2. So I'm going to change a lot. I'm just going to change lots here, but the methods that I've used here is the substitution I've chosen to do, and the way you multiply out those brackets. This stays when you do this. When you do this question, you will have you will do the you will do sine, cosine, and that you will write out the substitution. So 1 over 1 plus x. You know the expansion. 1 over 1 plus u. You know that it is 1 minus u plus u squared, etc. You will say that 1 over cosine x is 1 over 1 plus 1 minus u squared over 2 plus u to the power 4 over 4. And thus, sorry, not u, of course, x. And then you use the substitution. Substitution u is equal to this. And you place that into here. Okay. I hope that makes more sense. I'm very sorry for this was an impromptu decision to do the cotangent instead of tangent, and it backfired completely because, of course, you have to check before you do a Taylor expansion. You have to check that actually the function does exist at that point. Because if the function not exist at that point, then from the very beginning, you have the Taylor expansion starts with this little guy here. So f of x is that plus the first derivative times x. Now, if this does not exist, then no, it won't work. You have to find the expansion at a different point. To get an approximation, you have to do it at a different point. Does it make sense? All right. So does that make sense? Do you have any questions about the Taylor series or any questions at all? Do let me know. So in physics, it's going to be, so we're not going to do the LC circuits, not this year. We, so the last topic, where is it? The last math topics is going to be combinatorics and a little bit binomial expansions. And for physics, we're going to do electrostatics. So we'll move LC circuits to next year. Usually, yes. Like all the expansion by default, it is radians. By default, it's radians. So combinatorics for maths and electrostatics and capacitors for physics. That's the last. Okay. All right. So I'll see you next week then. Okay. Bye.